Hello, and welcome to this lecture in my series on the satisfiability problem for fragments of first-order logic. My name is Pratt-Hartmann, and today I'll be talking about the fluted fragment. I shall show that the satisfiability problem for the fluted fragment is decidable, and I'll establish an upper complexity bound. As usual, I'll assume basic knowledge of first-order logic and complexity theory, and I'll try to explain the basic ideas behind the proof. If you want to go through the proof line by line, then I refer you to my book here, Fragments of First-Order Logic, published by Oxford University Press, section 6.3. So I'll start off by explaining in intuitive terms what the fluted fragment is, and I'll give a formal definition, and finally we'll go on to describe the satisfiability procedure. In the fluted fragment, which I'll denote here FL, the order of quantification of variables coincides with the order in which those variables appear as arguments of predicates. Here are two examples of fluted sentences. No lecturer introduces any professor to every student. I've written as a formula here. So we have three variables, x1, x2, x3, they're quantified in numerical order. And you'll see here, for example, we have the variables x1, x2, x3 appearing in that order as arguments of a predicate. Second example, no student admires every professor. We have two variables, x1, x2, quantified again in numerical order. And in this atom, you'll see that the variables appear in exactly that order. That's the rough idea. If we move bits of formulas around, then we can always line up the variables in fluted formulas so that they appear in columns. So here, this is the example which says that no student admires every professor. And you see I've simply put line feeds and tabs in so as to line up the variable x1, line up all occurrences of the variable x1 and all occurrences of the variable x2. And similarly for this formula here, no lecturer introduces any professor to every student. I've managed to, by judiciously moving things around, I've managed to line up the x1, x2 and x3 in columns. The illusion here is presumably architectural, so this is meant to resemble, I think, a fluted column or a champagne glass or something. Okay, so that's the basic idea behind the fluted fragment. You'll notice that in the fluted fragment, all atoms are of the form a predicate P applied to an appropriate number of arguments, where those arguments form an increasing contiguous sequence in their indices. And furthermore, Boolean combinations can only be formed by formulas whose the last free variable is the same. And thirdly, only the last free variable of a formula may be quantified. So if we have a look at our two examples, no student admires every professor, you'll see that I have a contiguous sequence of variables, x1, x2, trivial contiguous sequence of variables x2. Because the last free variable is the same, I can form a Boolean combination, and then I can quantify the last free variable. Now the last free variable of this subformula is x1, and so I can form a Boolean combination with another formula whose last free variable is x1 and quantify the last free variable, namely x1. And this example works exactly the same, except that I've got three variables here. Notice I have, in this subformula, I have a Boolean combination of two subformulas, and in both cases the last free variable is x3. So I can form Boolean combinations in that way. So we need to codify this and make this a little bit more precise. But first, again, just to give some idea of what you can do in the fluted fragment. As with the two-variable fragment of first-order logic, you can see that the fluted fragment subsumes ordinary propositional modal logic K under the standard translation. So if you have a propositional multimodal formula propositional multimodal logic, then if you translate that into first-order logic using standard Kripke semantics, then you will obtain a fluted formula. On the other hand, the following formulas are not in the fluted fragment for all x1 are x1, x1. This is not allowed because you don't have an increasing sequence. For all x1, for all x2, rx1, x2 implies rx2, x1. Again, this is a forbidden sequence. And this last formula here, for all x1, for all x2, rx1, x2 implies for all x3, rx2, x3 implies rx1, x3. Again, this is this last atom that violates the conditions on fluting because this isn't a contiguous sequence. So, in fact, it can be shown that reflexivity, symmetry, and transitivity are none of them expressible in the fluted fragment. Certainly these formulas are not fluted. Clearly, if you have at most one variable, then fluting doesn't make any difference. Propositional fluted logic is just propositional logic. One variable fluted logic is just one variable logic. So now for the formal definition. So we fix a sequence of variables x1, x2, x3, x4. We'll always be using these as our variables. And for all m greater than or equal to 0, we'll say that a fluted M atom, point to it, a fluted M atom is an expression consisting of a predicate followed by an increasing contiguous sequence of variables of the appropriate arity. So finishing with xm. Right, so if the predicate is of arity m minus l plus 1, then it starts with xl. Okay, and we allow the case L equals m plus 1. In other words, we allow the empty sequence. In other words, we allow the case of nullary predicates or proposition letters. So predicates in fluted, there's no limits at all on the arity of predicates in fluted logic. We don't allow equality as a predicate. As I mentioned earlier, this could be added, but it's a bit simpler if we don't. Now we define, that defines the notion of a fluted M atom. We define the set of formulas FL square brackets M for natural number M by simultaneous structural induction as follows. Any fluted M atom is a formula of FL square brackets M. FL square brackets M is closed under Boolean combinations. And if phi is in FL square brackets M plus 1, then, there exists x m plus 1 phi, and for all x m plus 1 phi are in FL square brackets M. So you see this is a simultaneous, infinite collection of structural inductions. The set of all fluted formulas is simply the union of the FL square brackets M, where M is a natural number. Now, we'll denote by FL superscript M without the square brackets the subfragment of the fluted fragment consisting of those formulas featuring at most M variables, free or bound. In other words, FL superscript M is equal to the intersection of FL, the fluted fragment, and the M variable fragment of first-order logic. Do not confuse FL superscript M with FL superscript square brackets M. So this sentence, which I mentioned earlier, is in FL M without the square brackets for all M greater than or equal to 3, because it's a fluted sentence and it is in the 3 variable fragment, therefore it's the K variable fragment for all K greater than or equal to 3. So clearly in FL M without the square brackets for all M greater than or equal to 3. However, it's in FL square brackets M only for M equals 0, because you see what happens here is that this is in these formulas, this subformula here is in FL square brackets 3. I quantify x3 and then in FL square brackets 2. So I can form Boolean combinations with this thing, which is in FL square brackets 2, and then quantify x2, and then I'm in FL square brackets 1, and so on, all the way. Once I've quantified x1, then I'm in FL square brackets 0. I might mention that for quantifier-free formulas, there's no difference between FLM and FL square brackets M, but that's really just a technical detail. I think the thing to realise here is that FL square brackets M is simply an auxiliary device which you use to formally define the fluted fragment, and FL without the square bracket, FLM where there are no square brackets, those are the formulas we're really interested in, namely the M variable fluted formulas. And so that's what we'll be concentrating on at the moment, the M variable fluted formulas. So, next idea, we need a notion of normal form. An FLM formula, an M variable fluted formula, is in normal form if it has the shape shown here. We have collection of universal quantifiers, m minus one of them, and then a conditional. The antecedent of the conditional is a quantifier-free fluted formula in m minus one variables, and then we there exists xm, and then the consequent of the conditional involves this quantifier-free formula gamma in m free variables. So this says, for all tuples x1 up to xm minus 1, if those things satisfy the quantifier-free formula mu I, then there exists xm such that they satisfy gamma I, and we have a collection of such formulas where I is in some index set, big I. And then these conjuncts here are similar, except that we don't have existential quantifier in the consequent of the conditional, but a universal quantifier. As usual, we shall call these conjuncts the existential requirements, and these conjuncts here, the second set of conjuncts, the witness requirements. The universal constraints. Get that right. So once again, existential requirements and the universal constraints. Okay, so that is a normal form fluted formula a normal form M variable fluted formula. Notice that all normal form M variable fluted formulas are by definition sentences. They have no free variables. Okay, and it should come as no surprise that we have a lemma. Let phi be a M variable fluted sentence. M greater than or equal to 1, we can compute in time bounded by a polynomial function of the size of phi, a normal form FLM formula satisfiable over the same domains as phi. So the proof of this lemma, in other words, we can reduce any formula to a normal form formula, and if we're interested in satisfiability or finite satisfiability, we get the same answer. So we can this lemma says that we can restrict attention when testing for satisfiability to normal form formulas. The proof of this lemma proceeds via rewriting techniques similar to those used for the normal form lemmas for the two-variable fragment and for the guarded fragment. There's absolutely no point in my repeating those here. I refer people to the lectures on the two-variable fragment and the guarded fragment for more information on this technique, but it's quite straightforward and it's left here as an exercise. Okay, so we have a normal form lemma. Now, it's important to realise that fluting allows us to delete variables from formulas entirely. So here are the two examples of fluted formulas that we had earlier, and I've highlighted the variables in blue. Well, clearly, anyone could have told you what those variables were going to be. You have absolutely no choice as to what to write, where to write the variables. In particular, you have no choice as to how to order the variables here in these atomic formulas. So we can delete them. They don't really contain any information. And if we can delete the variables, then we can remove the parentheses and commas and move everything up. So we get that rather neater form here. So we can always write formulas without variables at all. If you like variables, you can always put them back in, and there's a straightforward algorithm for how to do so, and that will give you a unique result up to variable renaming. I mean, you don't have to start with x3 here. If you started with x572, then you'd also get a sentence in the fluted fragment, but you can use smaller variables if you like. You can do that straightforwardly. Okay, so we'll use variable-free notation in the sequel wherever we can. So let's see how normal form formulas look when we do this. So here's a standard normal form formula. Right? We've got the existential requirements and the universal constraints. I've written it all on one line here to make it more compact. So let's identify the variables. Remember, these quantify-free subformulas will contain variables. You can't see them, they'll be there. So imagine they've been made blue as well. So we'll remove these because they don't contain any information, also from the subformulas, of course, the quantify-free subformulas. Remove all the variables and they tell us anything, and then we'll move everything up so it's nice and compact. So you'll see here that you've got for all m minus 1 times, and similarly here, well, we can replace that with a more compact notation for all superscript m minus 1. That's just, and again here, so that's just a little bit neater. So we'll write normal form formulas in that way. Now, it's not difficult to see that the two-variable fluted fragment has a satisfiability problem in ExpTime. Why? Well, because it's known that the satisfiability problem for the two-variable fragment is in ExpTime. We showed that in an earlier lecture in this series. And the two-variable fluted fragment is trivially a subset of the two-variable fragment, so certainly the upper bound applies. In the sequel, we're going to show that for any m-variable fluted sentence with m greater than or equal to 3, we can compute an m-1 variable fluted sentence with the following properties. So if you call the original sentence phi, and the sentence we compute psi, we require that, we require that phi is satisfiable if and only if psi is satisfiable, and phi is finitely satisfiable if and only if psi is finitely satisfiable. So given any f of m variable fluted sentence phi, we can compute an m-1 variable fluted sentence psi such that phi is satisfiable if and only if psi is satisfiable, and phi is finitely satisfiable if and only if psi is satisfiable. So this is like a reduction from the m variable fluted fragment to the satisfiability and finite satisfiability problems for the m variable fluted fragment to the corresponding problems for the m-1 variable fluted fragment. However, it will turn out that psi, the formula in the m-1 variable fluted fragment, is exponentially larger than phi, features an exponentially larger signature, and takes exponential time to compute. So what this will establish is that the fluted fragment has the finite model property, and that the satisfiability problem for the m variable fluted fragment is in m-1 ExpTime for m greater than or equal to 2. So this is because the two variable fluted fragment is in ExpTime, and you can reduce the m variable fluted fragment for m greater than or equal to 3 to the m-1 variable fluted fragment, the way which preserves satisfiability and finite satisfiability. So in fact we can improve on this complexity bound very slightly, and I'll just mention that below, but that's a detail. Okay, so let's see how this exponential reduction from the satisfiability problem for the m variable fluted fragment to the satisfiability problem for the m-1 variable fluted fragment works. So let phi be a sentence of the m variable fluted fragment, and we may assume that phi is in normal form. Remember, normal form we write in our variable free notation like this. We can assume without loss of generality that phi features no proposition letters, that is nullary predicates, because their truth value can simply be guessed. So what we'll do is introduce some new predicates. These predicates will have arity m-2. Remember, we're assuming that m is greater than or equal to 3 here, so these are new predicates of arity at least 1. So we'll introduce these new predicates of arity m-2, and I'll call these predicates p subscript I big J prime and q subscript big J prime, where I is one of the indices of the witness of the existential requirements, and J prime is a subset of the set of indices of the universal constraints in the formula phi. So you'll see that we have exponentially many predicates p subscript I comma big J prime, and exponentially many predicates q subscript big J prime. These will be new predicates which I'm going to introduce. The intended interpretations of these predicates are as follows. P I subscript I big J prime characterizes those m-2 tuples A bar such that for some A, the m-1 tuple consisting of A followed by A bar satisfies the antecedent of the ith witness requirement, the ith existential requirement, and the antecedents nu j of all of the universal constraints indexed by j in J prime. So it will satisfy Pij characterizes those m-2 tuples A bar such that for some object A, the m-1 tuple A bar satisfies mu I, this formula here, and all of the nu j's for j is in the subset J prime. So J prime, remember, it's a subset of J. Okay, and similarly, the predicate Qj big J prime characterizes those m-2 tuples A bar such that for some object A, the m-1 tuple A bar satisfies the formulas nu j for j is in for every j in the subset big J prime. So those are my new predicates. Remember, I was starting off with this formula in the m variable fluted fragment, and I want to produce an equisatisfiable formula in the m-1 variable fluted fragment. And to do that, I'm going to help myself to these new predicates and I've characterized, which have the intuitive interpretations just outlined. Okay. Now, we need to adapt the notion of atomic k-types employed in earlier lectures to the fluted fragment. So let sigma be a finite, purely relational signature in which all predicates have arity at least 1. A fluted k-literal over sigma is a fluted k-atom over sigma or its negation. So it has to be fluted, right? So the variable arguments have to be simply a sequence of, there have to be a suffix of the variable sequence x1 up to xk. A fluted k-type is a maximal consistent set of fluted k-literals over sigma. So thus, a fluted k-type is like an atomic k-type, except that we ignore literals that are not fluted. For example, we ignore literals like px1x1 or px2x1 or px1x3. And of course, because these are k-literals, we're talking about k-literals here, we require that the last variable always be xk. So the first variable needn't be x1 because you may have arity lower than k, but the last variable always has to have be xk. So we need a small technical lemma regarding these types. Let's just have a look at this lemma. Let chi be a quantifier-free m-variable fluted formula over some signature sigma. And let's take a smaller signature sigma minus. We'll denote by chi circle the strongest quantifier-free m-variable fluted formula in the smaller signature entailed by chi. then chi, the lemma says, chi's circle can be computed in time bounded by an exponential function of chi. Moreover, if tor minus is a fluted M-type over the smaller signature, making chi circle true, then tor minus can be extended to a fluted M-type tor over the original signature sigma, making chi true. And the proof of this lemma is fairly straightforward. We write chi in disjunctive normal form, so chi is now logically equivalent to a disjunction of fluted M-types over the original signature, and let the set of types, fluted M-types appearing in that disjunction be delta. Now for any fluted M-type tor over the original signature, let tor circle be the fluted M-type over the smaller signature, sigma minus, obtained by deleting from tor all conjuncts involving predicates not in the smaller signature. So we just get rid of any unwanted literals. Okay, so now we can simply define chi circle to be the disjunction of tor circle for all tor in the set delta. And it's routine to show that chi circle has the required properties. So it's a fairly simple piece of propositional logic, really. Nevertheless, this lemma drives, in some sense, the whole decidability proof that I'm now about to give. In the sequel, we'll be interested in the case where sigma minus consists of all the predicates of sigma of arity strictly less than m. So we're going to get rid of the emery predicates in our original formula phi. Thus, if chi is a quantifier-free formula of m-variable fluted formula, then chi circle can't involve any literals featuring emery predicates, because we've got rid of them, they're not in sigma minus. And in terms of variables, that means that chi can't feature the variable x1, because any literal involving the variable x1 would have to be would have to involve an emery predicate, since it certainly involves the variable xm. That's the way the fluted fragment works. And in variable free notation, chi circle can be regarded as a set of quantifier-free fluted formulas using m-1 variables. So with variable free notation, you don't actually see the variables. So you don't really care or know, in some sense, whether the variables are x2 up to xm or x1 up to xm minus 1. And it's just an m variable fluted, quantifier-free fluted formula. Call the variables what you like. Okay, so let's now return to the reduction. We'll start with a formula phi in the m variable fluted fragment, and we can assume that this formula is in normal form. Witness requirements, now universal constraints. We want to compute an equisatisfiable m-1 variable fluted formula psi, so we'll show that if phi is satisfiable, psi is satisfiable, and conversely. So the first thing I've got to do is to define psi. Now, the formula psi will consist of four conjuncts. Each conjunct is itself a big conjunction, and it will feature new predicates. These predicates pi big J prime and q big J prime, which I mentioned earlier. So I'll go through the details in a moment, but just to give you some rough idea, let's start with some rough idea of what these conjuncts do, so you get some orientation. So the first conjunct essentially establishes the meaning of the predicates pi big J prime. The second conjunct establishes the meaning of the predicates q big J prime. The third conjunct will ensure that when we construct a model of our original formula phi, the witness requirements will all obtain. And the fourth conjunct will ensure that when we construct a model of our original formula phi, the universal constraints will obtain. Okay, so that's the four conjuncts of psi. So let's suppose that phi is satisfiable. We'll show that psi is satisfiable. And if phi is satisfiable, let fractor A be a model of phi. Now, in order to construct a model of psi, I have to interpret the predicates p, I, big J prime and q, big J prime. And I'll do that as I advertised a moment ago. In other words, I'll expand our model A to one interpreting these new predicates as follows. The interpretation of p, I, big J prime will be the set of m minus 2 tuples in our domain, such that for some object in the domain, the m minus 1 tuple A bar satisfies mu I. Remember, that is the antecedent of the ith witness requirement. And moreover, A bar will satisfy nu j for all j in big J prime. And remember, nu j is the antecedent of the jth universal constraint. And q, the interpretation of q big J prime will simply be the set of m minus 2 tuples, such that for some object A, the m minus 1 tuple will satisfy nu j. The m minus 1 tuple A bar will satisfy nu j for all j in big J prime. Okay, so I claim that if I expand our original model A of phi by defining predicates in this way, I will obtain a model of psi. So let's, here I've rewritten the rules for the expanding the model A to a model A prime. So these are the interpretations of the new predicates. So that's just so we can refer back to them. And I've got to show, the first thing to show is that the first conjunct of psi is true. So this is the first conjunct of psi, the one defining the predicates pi big J prime. And this is quite straightforward. Suppose in our model A prime, the m minus 1 tuple A bar satisfies mu I. So A bar here is an m minus 2 tuple. Okay, so suppose the m minus 1 tuple A bar satisfies mu I. And furthermore, suppose it satisfies also nu j for all j in big J prime. Well, since A prime is just an expansion of A, those things will also be true in the original model A. But by construction of A, if you look at how I've defined the predicate here, I've defined this predicate pi big J prime to hold of all m minus 2 tuples, such that for some A these conditions hold. Well, in that case, the m minus 2 tuple A bar will satisfy A big J prime. And notice here, it's slightly confusing. This predicate is an m minus 2-ary predicate. We're using here variable free notation in the m minus 1 fluted fragment. So the implicit variables in this predicate are x2 up to xm. So this is I'm sorry, I've got that wrong, haven't I? The variables here, this is in the m minus 1 variable fluted fragment. So the variables here are x2 up to xm minus 1. And that's an m minus 2-ary predicate. So I managed to get the counting right this time. Okay, so since we're looking at satisfaction by an m minus 1 tuple A bar, that's all we have to show is that the m minus 2 tuple A bar satisfies pi J prime, and that it must by the construction of A prime. And so for the second group of contracts, that you proceed in exactly the same way. You can can show that the A prime makes the second contract true as well. That's just routine. Now let's look at the third conjunct. And the third conjunct says that if you've got an n minus 2 tuple, an m minus 2 tuple, satisfying pij prime, then you can extend that m minus 2 tuple with an object satisfying this formula here. And let's have a look at this formula. This formula says gamma I, in other words, it's the ith witness requirement of our original formula phi, together with delta delta j, and that's the consequent of all the universal requirements for all j in j prime. Okay, now this formula here, from gamma I to the end of delta j, is in the m minus 1, I'll get this right, it's in the m variable fluted fragment. Right? From the original formula phi, so it's in the m variable fluted fragment. So this wouldn't even be allowed, right? I mean, it's not even a sentence because you haven't got enough quantifiers for the number of variables. But remember this circle. What the circle does is it takes the strongest implied formula in the signature involving no emery predicates, and we can regard that as a formula in the m-1 variable fluted fragment, because in quantifier-free notation it's all the same. So this formula here, that is that conjunction with the circle applied, is a formula in the m-1 variable fluted fragments, and it's quantifier-free. And so this whole formula is a sentence, and it's perfectly fine. So it's a witness requirements. These are the witness requirements for psi, and they require witnesses of this rather strange kind. And the witnesses they require are like the witnesses required by the original formula phi. I mean, they have this gamma I, and they have all the universal constraints. That's a technical detail. They're like the witness requirements for the original formula phi, but the circle means that we get rid of all the predicates involved. We get rid of all predicates of arity m. Okay, so we need to show that in our extension A prime, fractor A prime, in our extended model, this formula is true, assuming that the original model A made phi true. Let's have a look. So suppose that we have an m minus 2 tuple A bar satisfying this thing, pi big J prime. We need to show that this consequent will also be true, will also be satisfied in A prime, fractor A prime. Why? Well, by the construction of, okay, we know that A bar is a tuple, an m minus 2 tuple satisfying pi big J prime. By the construction of A prime, in particular by the definition of the extensions of these predicates here, there exists an A such that the m-1 tuple A bar satisfies mu I and mu j and nu j, I'm sorry, for all j in big J prime. That's simply how we've defined this predicate. Okay, so in that case, since A bar satisfies mu I and nu j for all j in big J prime, well, from the fact that A is a model of phi, there must be a witness, right? And a witness for, since the antecedent of the ith witness requirement is satisfied by A bar, there must exist a B such that the tuple A bar B satisfies gamma I. And of course it will satisfy delta j for all j in big J prime, because all of the triggers, all of the antecedents for the universal constraints nu j for j in big J prime will be satisfied. So the witness will automatically satisfy them by the universal constraints for phi. So such an object B must exist. But then, if we take, suppose have a look at this. This is an m tuple, right? So there's an object, an m minus 2 tuple, and another object. So that's an m tuple. And if we add the circle to this formula, what that gives us is the strongest formula in the signature not involving any emery predicates, entailed by this thing, the thing without the circle. Well, then that must be satisfied by A bar B, because since this formula entails that formula, then we must have A bar B satisfying this. And notice we can forget the A, because there is no A anymore. We've only got m minus 1 variables. We've only got, yeah, I mean, all the variable x1 has gone away. Right? So we've relied this notation. We've sort of played on this variable-free notation a little bit here. Okay, so the n-1 tuple a bar b satisfies this, and if you look back to this formula, that's exactly what we require. We require, so given an n-2 tuple a bar satisfying pi big J prime, we can find an object B satisfying this formula gamma I and this big conjunction of the delta J with the circle applied to the whole lot, and that is therefore true. So this these sentences are all true in Fraktur A prime. Okay, so the fourth conjunct, which deals with the fourth set of conjuncts, which deals with the conditions for the requirements for the universal constraints, can be shown to be true in A prime similarly. So it's a very, very similar argument. Okay, so we've shown now that if phi is satisfiable, the original normal form fluted m-variable fragment formula is, if that's satisfiable, then this formula psi we've constructed, consisting of the four conjuncts, is also satisfiable. So what we've now got to show is the converse. Suppose that psi is satisfiable, then we need to show that phi is satisfiable. So suppose that A is a model of psi. Now what we'll do is we'll take S to be the number of elements in the index set I. And the index set I, remember, are the indices of the witness requirements in the original formula phi. So we just take NS will be just some number certainly bounded by the size of phi. What we'll then do is we'll take the n-fold Cartesian product of this structure A, and we'll call that B. Sorry, the s-fold Cartesian product of A, and we'll call that B. In other words, we duplicate all elements of the structure A s times, so that so we can always take s copies of every element. That's constructed in the standard way, as I explained in an earlier lecture. Okay, so since fluted formulas are equality free, then B also makes psi true. What we're going to do is we're going to expand B to a model of phi. And what do we need to do in order to obtain a model of phi? Well, we need to interpret the Emery, that's a mistake, that should be Emery predicates of phi, because psi doesn't contain any Emery predicates, but phi does. And we need to interpret these in order to obtain a model of phi. So what we'll do is we'll proceed tuple by tuple. Let's pick any m-1 tuple A bar from B. Well, so A bar is an m-2 tuple. Okay, so A bar is an m-1 tuple. Now suppose that for some I in the index set I, in our model B, A bar satisfies mu I. Mu I, remember, is the antecedent of the ith witness requirement of phi. And suppose further that big J prime, will let big J prime be the set of indices J such that A bar satisfies nu J, and remember that nu J is the jth the antecedent of the jth universal constraint in the original formula phi. And so what we're going to do is we want to make this original formula phi true. This is phi. We need to make it true. So we need to pick, since we have a tuple A bar satisfying mu A bar. Okay, so this is the mu I A bar, right? So so this is mu I is the antecedent of the ith witness requirement. We need to ensure that there is an object which satisfies gamma I. I mean, we also need to ensure it satisfies delta J for all J in big J prime, where big J prime is a set of indices satisfied by set of indices of formulas nu j satisfied by a bar. Okay, so we need to pick this element b so that it satisfies gamma I and ensure that it satisfies all the delta j, the appropriate delta j. How do we do that? Okay, so by assumption, a bar satisfies mu I and nu j for all j in big J prime. Now, this is one of the conjuncts of psi. So, from this conjunct, it follows that a bar satisfies p I j bar. Remember that this is an m-2-ary predicate. So the object A now doesn't come into this at all. So the tail of this m-1 tuple has to satisfy p I j bar, and that's just the object's, the m-2 tuple a bar. Okay, so a bar satisfies p I j prime. Now look at the third conjunct of phi. It will contain this thing. It says for all I in I, or all big J prime subset of J, if some m-2 tuple, let's say a bar, satisfies p I j prime, then there exists an object satisfying this. So we can find B such that this stuff is satisfied by a bar B. Okay, so what is this stuff? Well, it's just this formula gamma I and all the delta j for j in big J prime, and we apply the circle to it. So remember, these are m-1-ary formulas, or formulas in m-1 variables, because the thing inside the brackets is in m variables, but when you apply the circle, you get rid of all m-ary predicates. So it's effectively a formula in m-1 variables. And again, we're playing on the variable free notation here a little bit. Okay, so a bar B satisfies that. Now, we know that a bar B satisfies this thing in the structure B. So that means let's take the let Tor minus be the fluted type of a bar B in the structure B. And so that clearly entails the formula satisfied by the tuple. Now, by the lemma, this technical lemma we proved, we can extend Tor minus to a fluted type Tor entailing that. And now what are we going to do? We're going to assign a bar B the fluted type Tor. And we can do this because there will be a fluted type Tor extending the fluted m-1 type Tor minus. So Tor, remember, is a fluted M type. And we can assign that to a bar B. Effectively, we're defining the extensions of predicates of arity M, because the smaller signature, sigma minus here, is just the signature sigma with all the predicates of arity M removed, essentially. So we can now we'll apply that lemma, and we can assign this thing the fluted type Tor, and that will be completely consistent with B. So we're extending B. Okay, so since every element of B is copied at least cardinality of I times, we can choose distinct witnesses for each of these, for each I and I, so that when we fix fluted M types in this way, we never redefine things, so we never tread on our own toes, and so we never get any clashes. And we can carry out this assignment for every tuple a bar. So at this point, we've now found witnesses for everything we need. Right? So if a tuple we've defined we've set the fluted M types of a collection of tuples so that everything has a witness. Every m-1 tuple has an appropriate witness as required by phi at this point. Okay, so that's what I've just said. We've partially defined an expansion B prime of B by defining the fixing some of the extensions of the m-1 of the Emery predicates, arity M predicates. And we've ensured that this is true. Moreover, when we assigned the fluted M types of tuples, then we never violated, we were careful never to violate any of the universal constraints. So far, all of the universal constraints are true. Now, we've almost finished. The only thing we have to do is to complete the definition of our expansion B prime of B in such a way that the universal constraints of phi are not violated. Right, we've satisfied all the witness requirements. We haven't violated any universal constraints yet. We just need to complete the definition of any any M tuples whose M types have not been fixed in such a way as not to violate the universal requirements, and that's easily obtained using the fourth conjunct of psi, essentially using the same argument as we did here for the witness requirements. So in the resulting expansion B prime of B, we have a model of phi. If psi is satisfiable, so is phi. Okay, and that finishes the proof. And we notice also that B prime is finite if A is. So if phi is finitely satisfiable, so phi is not only satisfiable if and only if psi is, but phi is finitely satisfiable if and only if psi is. Okay, so let's put everything together. Starting with the formula phi1 equals phi in the M variable fluted fragment, we can find a formula phi2 in the m-1 variable fluted fragment such that phi2 is, excuse me, there's a typo, is finitely satisfiable or satisfiable if and only if phi1 is. Of course, phi2 is exponentially larger than phi1 over an exponentially larger signature, and it takes exponential time to compute it. So what we can now do is iterate the procedure, and eventually just keep working down, and we eventually obtain a formula fm-1 in the two variable fluted fragment, such that phi m-1 in the two variable fluted fragment, such that phi m-1 is finally satisfiable if and only if phi1 is, with phi2 m-tuply exponentially larger than phi over an m-tuply exponentially larger signature. But phi m-1 is in the two variable fluted fragment, and so if satisfiable, has a model of exponential size in the size of phi m-2. So in that case, phi 3 up to phi m all have finite models, and they're a little larger actually than the model for phi 3, but it doesn't. The increase is quite small. It doesn't really affect the orders of exponentials. So we can show that if phi is satisfiable, then it has a model of m-1-tuply exponential size. And you have to do the arithmetic to be completely sure of this, but it's straightforward. So we've proved the following. If m is greater than or equal to 2, then any satisfiable formula of the m variable fluted fragment has a model of size bounded by an m-1-tuply exponential function of the size of phi. Hence, the satisfiability problem for the m variable fluted fragment is in m-1 ExpTime. Actually, we can do a bit better than that. It's possible to show, using a construction essentially similar to that employed for the satisfiability problem for the two variable fragment here, that any satisfiable formula phi of the three variable fluted fragment has a model of size bounded by an exponential function of phi. So for three variables, you only need exponentially large models. So we can improve to see above size bound as follows. If m is greater than or equal to 3, then any satisfiable m variable fluted formula has a model of size bounded by an m-2-tuply exponential function of phi. Hence, sat FLM is in m-2 ExpTime. So we can shave an exponential off. but that's a detail, and proving this thing about three variable fluted fragment is routine and doesn't really add much new. We don't quite have a matching lower bound here, though we can show that the tower of exponentials increases without limit as the number of variables goes to infinity. So what we can show is that the satisfiability problem for the m variable fluted fragment is m divided by 2 rounded down n ExpTime hard for all m greater than or equal to 1. So I'm not going to give the proof of this formula. It's rather technical and quite difficult, but we can obtain a theorem which gives a lower bound on complexity, and as the number of variables increases every time by 2, the number of exponentials, the order of the exponential increases by 1. So we do have a tower of exponentials, and it follows from the above theorem that for m greater than or equal to 3, the complexity of the satisfiability problem for the m variable fluted fragment is somewhere between m divided by 2 n ExpTime, rounded down n ExpTime, and m minus 2 ExpTime. So this gives you tight complexity bounds up to m equals 4. And the cases of m equals 1 and 2 are straightforward. This gives tight complexity bounds up to m equals 4, and at the time of giving this lecture, it's not known how to close the complexity gap for m greater than or equal to 5. I'll finally say something about the history of the fluted fragment. So the fragment originates in an address given by W.V.O. Quine to the International Congress of Philosophy in Vienna in 1968. And Quine defined the homogeneous M-adic formulas. So basically they're the fluted formulas in which all predicates have arity m. So if you're looking at the m variable case, all the predicates have arity m, no lower arity predicates at all. And he later generalized this to what he called the fluted schemata. A formal definition of the fluted fragment along the lines we've used here in this lecture was given by William C. Purdy in 1996, and Purdy proved the finite model property. And that's the definition that stuck, and it's the one we've used here. Actually, if you look back to what Quine wrote, I mean, he wrote everything out in English, and it was not really formally defined. And it may well be that Quine had something else in mind, possibly the so-called ordered fragment, which was later independently discovered by Andreas Herzig in 1990. But the name, the fluted fragment, has now really stuck to Purdy's definition, and that's what we'll take it to be. Can't change the name now. Actually, in a later paper, William Purdy showed that claimed that the satisfiability problem for the whole of the fluted fragment is in n ExpTime. This claim is not correct, as shown by the lower complexity bounds mentioned just a few moments ago. And those were given in a paper by myself and Lydia Tendera and Wiesław Schwast in 2019. Finally, I should mention that the fluted fragment can be extended. In particular, it can be extended to the so-called adjacent fragment, which also subsumes the ordered fragment of Andreas Herzig, incidentally. And in the idea of the adjacent fragment is that instead of requiring that the variables occur in increasing order, the indices of variables as in arguments to predicates occur in increasing order, they are simply subject to the constraint that neighbouring variables differ in their indices by at most 1. So that's the adjacent fragment, and it was shown just the other year by myself, Bartosz Bednarczyk and Diamantis Karyelis, that the adjacent fragment also has a decidable satisfiability problem with a similar pattern of complexity bounds.